Welcome to ATMOS 5000 Day 28. Our objectives today are being pulled from Chapter 21 of the Stull textbook, Sections 21.1 and 21.2. We're also going to finish up with Beer's Law, which was the last of the black-body radiation laws from Chapter 2, Section 2.3. The Chapter 21 focuses in on the climate system, and in order to do that, we have to understand radiative equilibrium, and then we'll create simple model representations of the radiative balance that the Earth is in with the Sun. And then we'll go into the details about what controls Earth's climate. And then we'll look at the data that scientists use to determine Earth's past climate history. So here we have a beam of radiation with an irradiance E0 coming into a slab of atmosphere. And as it passes through this slab of atmosphere, some of the radiation is scattered and some is absorbed. This scattering and absorption happens by both gases and particles. And so that the beam of radiation, as it exits this slab of radiation, has been depleted somewhat or attenuated somewhat, in this case by delta E. So what Beer's laws does is it actually comes up with a way to quantify the amount of radiation that's actually transmitted through this layer. So we have several different forms of Beer's law, and there's a lot of material here. The very first one is that the irradiance transmitted is equal to the incident irradiance times the exponent of minus NB times delta S. Now I need to define some terms. N is the number density of particles or gases in the atmosphere, and B is the extinction cross-section of each particle or gas. So it's essentially how big it is from the perspective of incoming radiation. And delta S is the path length through the slab of atmosphere. So the first equation in this list basically looks at the effect of scattering of light and how that attenuates the radiation. The second equation, which looks very similar to the first, except for instead of having N and B, it has K and rho. K is the extinction coefficient for absorption of an absorbing gas or particle, and density is the density of the absorbing species, not the density of the atmosphere, but the density of the absorbing species. So the second equation in this list of equations is looking at the impact of atmospheric absorption by particles and gases. And then the third equation kind of puts it all together, where we have the amount of radiation that is transmitted through the atmosphere is essentially going to be equal to the amount that was incident times the exponent of minus tau extinction. And tau extinction is what we refer to as the optical depth. And the optical depth, of course, if you look down at the fourth level, is contributed by the optical depth due to absorption by particles, AP, plus the optical depth due to absorption by gases, AG, plus the optical depth due to scattering by particles, SP, plus the optical depth due to scattering by gases. And the other equation that is here is delta S, where S is equal to the normal path length, and secant of the zenith angle will give you the entire path length, the slant path length through the layer. So that when the zenith angle is 0 and you have a direct overhead sun, then the secant, of course, is 1 over cosine. So the 1 over the cosine of 0 is equal to 1, and so you'll end up with the value of S for a directly overhead sun. But as the zenith angle increases, then the path length will increase commensurately until you end up with a zenith angle of 90, at which point you have an infinite path length. Scattering of radiation. We're not going to be able to go into the details of how to calculate scattering, but we will look at the qualitative properties associated with scattering. And the first thing to note is that everything in the atmosphere scatters radiation. all gases and all particles scatter radiation. They don't all do it as efficiently as each other, but they all do contribute to the scattering. Particles scatter visible light radiation much more effectively than gases, and the particles that scatter the radiation the best are the ones that have a effective diameter that is about the same as the wavelength of the radiation that's incident. So this would be, since if you think of green light being 0.5 micrometers, then it's kind of the submicron 0.5 to kind of 1 micrometer particles that have the highest scattering efficiency. The particles don't necessarily scatter the light equally in all directions. They tend to scatter the light in the forward and to the lesser degree backwards directions, with less scattering in the side directions, so that the phase function of the light scattering actually kind of looks like a guitar body, an acoustic guitar body. And as the particles get bigger, the fraction of the radiation that's scattered in the forward direction gets bigger. So the biggest particles very much scatter in the forward direction. And when you have particles in the atmosphere, if you look towards the sun and it's very hazy, and then you turn your back to the sun and the visibility is better, that's an example of this phase function of the particle scattering, because when you're looking at the sun, you're looking into the forward scattered light. When you put your back to the sun, you're looking at the backward scattered light. And that's an example of scattering by particles. Gases do scatter light, but they're more effective at scattering shorter wavelengths rather than longer wavelengths. So if you think about gases in the atmosphere that scatter the different wavelengths of visible radiation, the shortest wavelengths of visible radiation are the blues, and the longest are the reds. So these gases that are in the atmosphere are more effective at scattering blue light than they are red light, and that is one of the contributing factors to creating the blue sky. The other thing to note about gases is that they scatter light equally in all directions. So their phase function is kind of like a perfect sphere. Absorption of radiation. So the odd oxygen molecules, the oxygen and O3, which is ozone, are good absorbers of certain wavelengths of ultraviolet radiation. However, most gases, with the exception of nitrogen dioxide, which is a pollutant in urban areas, are transparent to visible radiation. So the atmosphere is actually pretty transparent to visible radiation from a gas perspective. However, we do have darker particles in the atmosphere which can absorb solar radiation. The darkest of those is actually soot. And then there are some minerals, mineral dust in the atmosphere that also absorb solar radiation, that are not white, obviously. And then there are the greenhouse gases, the most common greenhouse gases being water vapor, carbon dioxide, methane, nitrous oxide, N2O, and chlorofluorocarbons. And these gases are transparent to visible radiation, but they absorb infrared radiation. So what is radiative equilibrium? Well, it's the statement that the incoming energy to a system is equal to the outgoing energy of the system. It can also be stated that absorption equals emission inside the system. And so if you have a radiative equilibrium where the incoming is equal to the outgoing or the absorption equals emission, then the temperature of the system will remain constant. So if the Earth is in radiative equilibrium with the sun, then the climate will be stable and the temperature will remain constant. If the Earth emits less energy than it receives, then the Earth's climate will warm. And if the Earth emits more energy than it receives, then the Earth's climate will cool. This is very analogous to your bank account. You have a savings account. If you spend more than you deposit, your bank account will go down, and if you save more than you spend, then your bank account will increase. That's the concept of radiative equilibrium. So here we have a very simplistic model of the radiative equilibrium between the Earth and the Sun. And we're going to assume that there's no atmosphere. And we're going to assume that the ground is a black body, which is a perfect absorber and a perfect emitter of radiation at all wavelengths. So we have the Sun, which has radiation that is reaching our planet, and the total amount of radiation that is being intercepted by our planet is equal to the solar constant S, which is 1,368 watts per meter squared, times the area of the disk, of the cross-sectional area of our planet. And the cross-sectional area of a circle is basically pi r squared, where r is the radius of the Earth. So you multiply pi r squared times the solar constant, and you'll end up with units of watts. So that's joules per second. And that defines the amount of energy that is entering into the system. Well, I guess I lied in that I was assuming that the Earth is a perfect black body. Well, it's not a perfect black body if it has a reflectivity. So in this case, it is a perfect absorber and emitter of infrared radiation, but it's not a perfect absorber of incoming solar radiation because it's actually reflecting some of that. And the reflectivity of the ground is defined by Rg. So that's Rg, the reflectivity of the ground, times pi r squared. S is the amount of radiation that is reflected off of the Earth's surface. And then consequently, the amount of radiation that's absorbed by the ground is 1 minus Rg. So it's whatever wasn't reflected is absorbed. And that's pi r squared times S as well. So that defines the shortwave radiation streams, the incoming, the absorption, and the outgoing. And on the right, with the red arrow, we have the long-wave radiation balance. So the long-wave radiation is radiation that's being emitted by the ground to space. And since there's no atmosphere, all of the radiation that is emitted by the Earth goes directly to space. And you might notice that the amount of energy that is emitted by an object is controlled by the Stefan-Boltzmann law, which is sigma times temperature of the ground to the 4th power. But then we have a multiplier out here in the front because the Stefan-Boltzmann law gives you essentially an irradiance watts per meter squared, where sigma is the Stefan-Boltzmann constant. And so that's watts per meter squared, but we need the answer in watts, so we have to multiply by the surface area of the sphere where all of this radiation is being emitted by. And the surface area of a sphere is 4 pi r squared, whereas the cross-sectional area of the circle for the shortwave radiation was pi r squared, because now the entire surface of the planet is emitting radiation. So we have essentially our incoming radiation, which is your pi r squared S. You have your absorption in the system at the ground, which is the 1 minus Rg times pi r squared S. And you have the reflectivity off the ground, Rg pi r squared S. And you have your energy, which is emitted, your long wave radiation, which is emitted from the ground as 4 pi r squared sigma Tg to the 4th. So let's apply our radiative equilibrium to this model. And the first equation there is basically equating the incoming radiation to the outgoing radiation. So the only downward arrow that we have in our system here is the incoming radiation. That's your pi r squared S. And then we have two streams of outgoing radiation. We have one short wave, which is the amount of radiation that was reflected off the ground. And then we have one stream of long wave radiation, which is the infrared energy being emitted by the ground. And so you set those equal to each other, and that's the radiative equilibrium of the system. Alternatively, you could do absorption equals emission, and we'll do this for the ground. The amount of radiation that is absorbed by the ground was the 1 minus Rg times pi r squared S. and the amount of energy that is being emitted by the ground is the 4 pi r squared sigma Tg to the fourth. Now, mathematically, you could massage the top equation and make it look like the second equation, and they both are essentially providing the exact same information. It's just a slightly different way to look at this. The top is incoming equals outgoing, where you keep track of every single radiation stream, and absorption equals emission. You only have to focus in on what is actually being absorbed and what is actually being emitted, and the reflected radiation basically gets, that stream gets incorporated in a slightly different way. So we have an equation. This equation has one unknown. If we specify the reflectivity of the ground, we know, then we would know Rg. We know the radius of the Earth squared, but that doesn't actually matter because you'll notice that in the radiative equilibrium equation, it has pi r squared in both sides. So you can eliminate the pi r squared. So the radius of the planet doesn't matter. S is the solar constant, which we know as 1,368 watts per meter squared. Sigma is the Stefan-Boltzmann constant, which we know. So we're left with one unknown, which is Tg. So let's solve for the Tg now. So in this no atmospheric model, we basically solve for the temperature of the ground, and it's going to be 1 minus the reflectivity of the ground times the solar constant divided by 4 sigma raised to the 1/4 power. And if we just go ahead and define the reflectivity of the ground as 0.3, so 30% of the incoming radiation is reflected off of the planet, then if you plug these numbers in, using the Stefan-Boltzmann constant, the appropriate value, then you'll get a temperature of the ground of 254.9 Kelvin, which is actually quite cold. So why is this model produce such a cold ground? I even know why. It's because it doesn't have an atmosphere, and the atmosphere must act to warm the surface of the planet. So let's create a little bit more sophisticated model so that we can determine what the impact of the atmosphere is and how that will impact the temperature of the ground. So let's take a look at a one-layer radiative transfer model. So in this case, we're going to treat the atmosphere as a slab that is above the ground. And the amount of radiation that is coming into the system way over on the left from the sun is going to be the same. It's your pi r squared S. And I know there's a lot of stuff here, but we're going to walk through from left to right all the way along, and we're going to follow the radiation streams until we get completed with them. So your incoming radiation is pi r squared S, and the atmosphere has a reflectivity, Ra, so some of that incoming radiation is reflected off of the atmosphere, and that's your Ra times pi r squared S. So the amount of radiation that's actually making it into the atmosphere is the amount that was not reflected. So it's 1 minus Ra times pi r squared S. And of that radiation that makes it into the atmosphere, some of that is being absorbed. And so that is the absorptivity A, and it's absorptivity of the atmosphere in the shortwave. So A, ASW subscript. That's the amount of radiation that's absorbed by the atmosphere. And the amount that's transmitted through the atmosphere is the whatever wasn't absorbed in the atmosphere. So it's 1 minus A for the shortwave times 1 minus the reflectivity of the atmosphere times pi r squared S. So that's the amount of radiation that is incident upon the ground, but the ground has a reflectivity, Rg. So some of that radiation is reflected off the ground. The amount that's reflected is Rg times the amount of radiation that was incident. So it's Rg times 1 minus A for the short wave times 1 minus the reflectivity of the atmosphere times pi r squared S. And when it comes up to the atmosphere, theoretically it would get reflected again, but we usually in this type of layer radiative transfer model will ignore multiple reflections. So we've already reflected off the ground, so we're not going to reflect off the atmosphere, but you could set up your model to where you basically have radiation that's reflected back and forth between the atmosphere and the ground, becoming ever smaller. But we're going to ignore that in this simplistic model. And so the amount of radiation that was absorbed by the ground is whatever wasn't reflected off the ground. So it's 1 minus the reflectivity of the ground times the amount of radiation that was incident upon the ground, which was the 1 minus the absorptivity of the shortwave of atmosphere times 1 minus the reflectivity of the atmosphere times pi r squared s. Now we have completed all of the streams of radiation for the shortwave radiation. Now we're going to move to the long wave radiation, which is the infrared energy. And we'll start off with the stream of radiation that is being emitted by the ground. Now remember, the amount of radiation that's being emitted by the ground is 4 pi r squared because it's being emitted over the entire surface area of the sphere times sigma times temperature of ground to the fourth. And that radiation is incident upon the atmosphere, and some of that is absorbed. So we have to include the absorptivity of the atmosphere on the long wave, ALW subscript. And then the amount that makes it to space is whatever wasn't absorbed by the atmosphere. So that's 1 minus the absorptivity of the atmosphere in the long wave times the 4 pi r squared sigma Tg to the fourth. And that completes the stream of radiation that is coming from the ground, that's being emitted by the ground. But the atmosphere has a temperature greater than absolute zero, so it's obviously emitting infrared radiation as well. And the amount of radiation that the atmosphere is emitting is also 4 pi r squared times sigma, and in this case it's the temperature of the atmosphere to the fourth, and it's emitting that radiation essentially to space, and it's also emitting that radiation, same amount of radiation, back down to the ground. So that completes the setup for our one-layer radiative transfer model, and the next step in the process is to use the radiative equilibrium assumption in order to create equations for this model. So here I've decided to write equations for the ground and for the atmosphere, and I've decided to use the absorption equals emission form of the radiative equilibrium equations. So if I look down at the ground, there are two streams of radiation that are being absorbed, one short wave and one long wave. So if in this equation, you can see that the amount of shortwave radiation that was being absorbed is the first term, and then the second term on the left of the equal sign, the 4 pi r squared sigma Ta to the fourth, is the amount of radiation that the ground is receiving from the atmosphere, and we're assuming that the ground is absorbing all of that. So we have two streams of absorbing radiation, and that's going to be equal to the amount of radiation that's emitted by the ground, which is the 4 pi r squared sigma Tg to the fourth. So that's a radiative equilibrium equation for the ground. And we can do the same thing for the atmosphere. And we have two streams of radiation which were absorbed by the atmosphere. We have a short wave stream and we have a long wave stream. So the first one is the absorption of the short wave, the ASW times 1 minus RA times pi r squared S. And the second one is the absorptivity of the atmosphere in the long wave times 4 pi r squared sigma Tg to the fourth. So those are the absorption, and then that has to be equal to the emission. And what's being emitted by the atmosphere? It's the 4 pi r squared sigma Ta to the fourth. So we have two equations, and let's take a look at what we know and what we don't know. So I can come up with values and constrain values for the reflectivity of the ground, the absorptivity of the atmosphere in the short wave, the absorptivity of the atmosphere in the long wave, the reflectivity of the atmosphere, and the solar constant, which is 1,368 watts per meter squared. If I know those values, or I specify those values, then it leaves me with two unknowns: the temperature of the atmosphere and the temperature of the ground. So I have two equations with the same two unknowns. I can then combine these equations and reduce the dimensionality from two variables that are unknown to one variable that's unknown, and be able to solve for that variable. So an obvious way to do this is in the equation for the radiative equilibrium for the ground. The second term is 4 pi r squared sigma Ta to the fourth. And in the equation for the atmosphere, we have that same term on the right-hand side of the equation. And so if I take the equation from the atmosphere and substitute into the equation for the ground, I will have removed one of the variables, in this case the temperature for the atmosphere, and I'll have one equation with one unknown, and then I can use algebra to solve that equation for the temperature of the ground. And if I do that, you can see down below the temperature of the ground is going to be equal to a whole bunch of terms times the solar constant divided by 4 times the Stefan-Boltzmann constant times 1 minus the absorptivity of the atmosphere in the long wave. And since I have specified the values for the reflectivity of the ground and the absorption of the atmosphere in the short wave and the absorption of the atmosphere in the long wave and the reflectivity of the atmosphere, I can plug those quantities into the equation for the temperature of the ground, and I came up with, for these particular specified values, a temperature of the ground of 288.8 Kelvin. So now that I have solved one of the variables that were unknown, I can then take that variable and substitute it back into the radiative equilibrium equation for the atmosphere, which is the second equation up above. And then by doing that, you'll see that I've now reduced the dimensionality of that equation to one variable, one unknown in one equation. And I can solve that equation for the temperature of the atmosphere. And here we have the absorptivity of the atmosphere in the shortwave times 1 minus the reflectivity of the atmosphere times the solar constant, plus the absorptivity of the atmosphere in the long wave times 4 sigma times the temperature of gravity, the temperature of the ground, sorry. And all of that is divided by 4 sigma. And all of that is raised to the 1/4 power. And when I do that, I get a atmospheric temperature of 239 Kelvin. So as we saw in the previous one-layer model of the Earth atmosphere system, the presence of the atmosphere actually acts to warm the surface quite significantly. So clearly the atmosphere is an important component of the Earth atmosphere system, but it all starts with the sun. And if we change the amount of radiation that we receive from the sun, that solar constant S, then it will have a dramatic impact upon the temperature of the ground and the temperature of the atmosphere. So we've been treating the solar output at the top of the Earth's atmosphere as 1,368 watts per meter squared, and we've been treating that as a constant. Well, we know from sunlight observations that the sunspot cycle alters the amount of solar output by about plus or minus 0.1%, which is plus or minus basically 1.37-ish watts per meter squared during that sunspot cycle. And we also know that there are long-term variations in the solar output. And the reason we know that is because we understand the life cycle of stars similar to ours. And these stars will gradually increase in luminosity until their fuel starts to become depleted, and then they'll go through one of several different outcomes for the sun depending upon the mass that it has. But based upon these long-term variation models of solar evolution, we know that the sun is now about 10% brighter than it was 65 million years ago during the age of the dinosaurs. So what controls the amount of energy that the Earth receives from the sun? Clearly, interstellar dust is going to be important. Once the energy is emitted by the sun, if there's interstellar dust between the sun and the Earth that absorbs some of that, then it would reduce the amount of radiation that we receive from the sun. And there's absolutely nothing we could do about that. The reflectivity or the albedo of the Earth also controls how much energy enters into the Earth system. And the reflectivity of our planet is primarily controlled by the cloud coverage and to a lesser extent by the ice coverage on the planet, by the types and amount of vegetation, the amount of urbanization that occurs, and by air pollution. So what happens to the incoming sunlight? So if we have 100% of the incoming solar radiation at the top of the Earth's atmosphere, about 30% of that is reflected off of either the atmosphere or the surface. So the clouds are reflecting about 6% of the incoming solar radiation. The Earth's surface is reflecting about 4%, and the atmosphere, due to the backscattering, is by gases is reflecting about 6%. You add all those together and you get about 30% albedo. Well, about 19% of the atmosphere of the solar radiation is absorbed within the atmosphere. A lot of that is ultraviolet radiation, but some of that is absorption inside clouds. And of that 100% radiation that's received at the top of the atmosphere, only about 51% of it is actually absorbed at the surface on average. So let's look at these contributions to the global albedo. The brightest objects on our planet are the thick clouds and fresh snow. Fresh snow can reflect up to 95% of the incoming solar radiation, as can thick clouds. If you have thinner clouds, they're much more transparent, and they can reflect anywhere from 30 to 50% of the solar radiation back to space. Water, on the other hand, is generally very dark and non-reflective surface. It only reflects about 10% of the incoming solar radiation on average, unless you happen to be at the specific angle where the angle of incidence equals the angle of reflection, and then the water can act as a mirror, but that's only at a very specific angle. Sand and deserts are generally pretty bright. They generally reflect more than 30%, up to 45% of the solar radiation. Grass, on the other hand, is more absorbing than desert or plowed lands, typically reflecting up to 30% of the solar radiation. And forests, because they're designed to maximize the absorption of solar radiation, are actually quite dark, and they only reflect anywhere between 3 to 10% of the solar radiation back to space. And of course, the global albedo is the sum of the contribution of the albedo from all of these different surfaces and clouds over the entire planet. So what happens to the outgoing infrared radiation from the Earth? Well, water is a good absorber of infrared radiation, regardless of whether it happens to be in the vapor phase or the liquid phase. And some of that outgoing infrared radiation is going to be absorbed by clouds. Some of it is going to be absorbed by greenhouse gases, with the dominant greenhouse gases being water vapor, which is by far the most abundant greenhouse gas, followed by carbon dioxide, which is the second most abundant greenhouse gas. And then there are other trace gases which act as greenhouse gases as well, including ozone, methane, nitrous oxides, and chlorofluorocarbons. And some of the energy that is emitted by the Earth's surface, some of that infrared heat energy does make it directly to space. So how does a greenhouse work, and why do we refer to these gases, which are transparent in the visible but absorb infrared heat energy? Why do we refer to these as greenhouse gases? Well, let's look at how a greenhouse works. So we have this enclosure with these transparent panes of glass, and the glass lets the sunshine energy in, and that sunshine warms the floor. And infrared heat energy is going to be emitted, but it's essentially trapped by the glass. And as the surface warms up, it starts to warm up the air inside the glass, or the air inside the enclosure, and convection inside the greenhouse will mix the air, and so that you end up with an overall warmer air inside the greenhouse. Let's compare this to the atmosphere and how the atmosphere works. So over here on the left, we have the solar radiation coming in, and we're going to look at the situation where we don't have any greenhouse gases. So the sun will basically be absorbed at the ground. The ground will heat up and will give off infrared heat energy. And if we don't have any greenhouse gases, then that infrared heat energy will be emitted directly to space. Well, if we have greenhouse gases in the atmosphere, then not all of that stream of outgoing infrared radiation is going to make it to space, because a lot of that energy is going to be absorbed in the atmosphere, and only a smaller fraction, denoted here by the thinner, smaller arrow, is going to be going to space. But of course, these greenhouse gases, having absorbed the solar radiation, are going to warm up the atmosphere, and that atmosphere is going to then be emitting some of that radiation back down to the surface. So with the greenhouse gases in the atmosphere, the surface is warmer than it otherwise would be. And that warming surface essentially causes convection, which can then mix the atmosphere. So there are some similarities between how the atmosphere behaves and the greenhouse gas and the greenhouse scenario, as shown in the previous slide. So do clouds behave similar to a greenhouse? Well, on the left, we have the no greenhouse gas scenario, where there's no absorption of the outgoing infrared radiation. In the middle, we have the greenhouse gas scenario, where those greenhouse gases are absorbing some of the outgoing radiation and emitting it some back down to space. Where for low clouds, well, these low clouds basically absorb the a significant amount of radiation coming from the surface, and they warm up. And because they're at a higher temperature, they're going to be emitting a significant amount of radiation back down to the surface, but they're also going to be emitting a significant amount of radiation directly to space, because these clouds are warm clouds, because they're low down in the atmosphere near the surface. And on the right, we have high clouds. So the Earth is still emitting its radiation. Those high clouds are absorbing the radiation, but these high clouds are much colder than the low clouds, so they emit less radiation back down to the surface, but they also emit less radiation to space. So yes, these clouds do behave in a manner similar to a greenhouse, in that they absorb some of the outgoing infrared radiation and emit it back down to the surface. But the amount of radiation that is emitted back down to the surface doesn't depend upon the concentration as it would with the greenhouse gases. It instead depends upon the temperature of the cloud top. If you have a cold cloud top temperature, you don't get much radiation to space. If you have a high cloud top temperature, then you'll be emitting a lot of radiation to space. So let's look at what controls the local climate. The most important things when it comes to the local climate is the latitude and the elevation. If you want to be warmer, move towards the equator. If you want to be colder, you move towards the poles, or you move up higher in elevation. Everything else after those two facts are secondary. Topography can play a role in local climate by funneling winds, or causing rain shadows, or causing upslope flow. Geography, your distance from the mountains or the water, Water has a high specific heat and doesn't change temperature very rapidly, so it will act to moderate the temperature swings between the seasons if you happen to be close to a large water body. The land cover has a big impact as well, whether or not it's ocean, ice, vegetation, or buildings. All of those things affect the reflectivity of the atmosphere in the short wave and can affect the local climate. And then we also have global atmospheric and ocean circulations. Ocean currents can have a big impact on local climate by transporting either warm water or cold water to a given location. So let's take a look at the average surface temperatures in January. This happens to be in degrees Fahrenheit, and you'll notice that in the northern hemisphere winter, the continents are much colder than the surrounding oceans. And in the southern hemisphere, which is their summer, the continents are much warmer than the surrounding oceans. And this has to do with the fact that the specific heat of the land masses is much less than the specific heat of the ocean. Therefore, the land masses can change temperature quicker in response to changing forcing as opposed to the oceans, which are much slower to respond. And if we look at the average surface temperatures in July, which would be the northern hemisphere summer, you see the reverse. You'll see that the continents in the northern hemisphere are warmer than the surrounding oceans. And in the southern hemisphere, you would think that the continents would be colder than the surrounding oceans, but there's just not enough mass in the southern hemisphere continents to really significantly alter the land temperature balance in the southern hemisphere for the winter time. So we've got all of these things. We have a good understanding now of what controls our climate through radiative equilibrium and what controls our local climate. The next question is how can we determine the history of Earth's climate? Especially since we only have direct temperature measurements that go back about 150 years, and we don't have global coverage even for that 150-year time period. So we have to use what we call proxies, which are indirect measurements that will give us information about past climates. And we use different types of proxy measurements depending upon the time frame that we're most interested in. For example, if we can use tree rings in order to understand the climate history over the last lifetime of the oldest tree that you can find. So somewhere in the 500 to 5,000 year range. I just put down 2,000 years maximum here. We do have bristlecone pines in the US that are up to 5,000 years old. If you want to go back further in time, we can use lake sediment cores. But most lakes are generally not much older than, at least around here, are not much older than the last glacial maximum, so 20,000 years worth of history. If you want to go back further in time, we can use ice cores, which can go anywhere from a couple 100,000 to a little over 1 million years. And then if you want to go further back than that, we have to go to ocean cores, which can get you back to about 200 million years. And it's impossible to find proxy measurements for anything beyond 200 million years, because at that point, even the bottom of the ocean has overturned and been replaced through the plate tectonics. So let's take a look at how trees can help us identify past climates. This is the study called Dendrochronology, which is the study of tree rings. These annual tree rings form in trees that live in areas with well-defined seasons. And the tree ring width is related to the availability of water and to a lesser extent temperature. And you can actually calibrate the growth based upon a combination of temperature and precipitation. Lots of available water yields wide growth rings, and drought yields very narrow growth rings. So if we look at a core, we have early wood, which is the light wood, which is when the wood is growing fast. It appears light in color, the cells are thin-walled and large diameter. And then you have late wood in the summer and fall, which is slower growing, and it appears dark in color. And the total ring width for a given year is a light and a dark band. So you put those together, and that's the growth for a single year. And you can see that the width of these growth bands varies from year to year in this example. If you want to try and understand the temperature using lake sediment cores, then you need to go out and collect a core of the mud from the bottom of the lake. And so here's an example from Weber Lake in northeastern Minnesota. And they were able to core back about 10 meters worth of mud. Of course, the top part of the mud is the newest, and the stuff at the bottom is the oldest. And they can actually radiocarbon date the objects in the mud, and so they can actually put a date stamp on as you move down in depth in terms of meters. So you can put date stamps on those. And then what you can do is at each one of those locations, you can take a slice of it and you can start looking at pollen, which is in the mud, which was deposited in the lake and sank to the bottom and got incorporated into the sediments. And you can identify, not only count the pollen, but you have to identify which species it comes from. And so, for example, at the very oldest part of this lake sediment core, down about 10 meters depth, more than 15,000 years ago, the dominant pollen was spruce trees and sage. And this happens to be during the Ice Age, when the temperatures were low and precipitation was different as well. And then as we came out of the Ice Age, you'll notice that the birch took off like crazy. Birch is considered a colonizing species, but that was eventually replaced by jack and red pine, which peaked at about 9,000 years ago. And then the jack and red pine were eventually replaced by white pine. So if you happen to be a biologist, you can determine which environmental conditions these different species actually thrive in. And so as the temperature changes, the species makeup is going to change as well. And so when we came out of the Ice Age, the sage basically pretty much went away and was replaced by other species. And it's not exactly like looking up on a thermometer and saying, oh, if we have this much birch and this much white pine and this much spruce, we have a certain temperature, but you can get ideas for how the temperature was changing over this time period using the pollen in the sediment cores. If you want to go back longer in time, we can use ice cores. And ice cores allow you to do two things. One is there are air bubbles that are trapped in the ice. And you can actually measure the composition of these air bubbles that were trapped in the ice to determine the carbon dioxide concentration of the atmosphere 100,000 years ago or 400,000 years ago. But the water ice itself contains information about temperature. There is basically isotopes of oxygen. There's the oxygen 18 isotope and the oxygen 16 isotope. And one of these is slightly heavier than the other because it has 2 additional neutrons. And so water that forms with oxygen 18 is referred to as heavy water, and and water that forms with oxygen 16 is basically regular water. And as it turns out, that when the oceans are warmer, they are able to evaporate more of the heavy water relative to the regular water. And so you'll end up with a larger oxygen 18 to 16 ratio when the oceans are warmer. And when the oceans cool off, that ratio decreases. So where's a good place to go to drill ice cores? Well, in the United States, you're kind of limited because we don't have a lot of places with glaciers. There's still a few glaciers left in Wyoming. There are a couple that are left in Montana, but Alaska has a good number of ice cores, of glaciers that still exist. But if you think about big picture, there's the Himalayas, there's the Andes in South America, and then you need to go to the really big places like Greenland and Antarctica. But by far the best place to get the longest record is the place where the ice has been locked up the longest, which is Antarctica. So here we have a map of Antarctica, and we have South Pole Station, which is basically sitting on almost 2 miles of accumulated ice, because every time it snows, it never melts. So it just piles up and up and up. And over the last 2 million years, the South Pole Station is now at 11,500 feet or so. But the Russians decided that they wanted to try and drill an ice core at the pole of inaccessibility, which is the point in the Antarctic continent that is furthest away from any ocean. And so it's the most inaccessible place and the hardest to get to. And so they decided that's where they wanted to drill, and that place is called Vostok. And they anticipated that this would be the coldest place in the world, and as it turns out, they were right. Welcome to Vostok. So Vostok is a drilling site. They have scientists down there, they have technicians down there, medical doctors, in order to deal with anything, because during the winter time it's impossible to evacuate anyone, so they have to be completely self-sufficient. They have to essentially have their electricity being generated in situ as well. So let's take a look at the annual temperature trend at Vostok. During the winter months, the temperature basically averages about minus 67 degrees Celsius. And during the summertime, it gets up to a balmy minus 32 degrees Celsius. This is definitely one of the colder places on the planet. So here's what they're after. They're after ice cores. So here we happen to have a section of the ice core that turned out to be 200 feet below the surface, and that corresponds to about a 700-year-old Antarctic ice core. So if you look on the right side, this is the youngest ice, and the left side is the older ice. And on the left side, you can basically see bands. And these bands actually kind of correspond to years. You have snow that falls, and then you have particles that end up on top of the snow, and then you have snow that falls the next year, and then you have particles that end up on top of it, and you end up with these bands that are identifiable in the Antarctic ice cores, much like tree rings. And the reason why you have white, why this ice core is white, is essentially that you have air that's trapped inside in terms of bubbles. And as the weight of the ice increases, it basically compresses the ice, increases the density of the ice, and compresses those air bubbles, eventually making them much, much smaller in volume. And the color of the ice actually changes from that milky white to clear, or essentially a dark blue. So here happens to be about 400,000 years worth of ice core data from the Vostok station. So we have two things that are plotted here. One is the temperature variation in blue as deduced from the oxygen 18 to 16 ratio. And then we have red, which is the carbon dioxide concentration that was directly measured by cracking open the bubbles in each of these layers of the ice. And what you'll see is that over the last 450,000 years, the Earth has spent much of that time in an ice age with low temperatures and low carbon dioxide concentrations. And the warm periods, the interglacial warm periods, which occur, about every 125,000 years, are rather short-lived, but they correspond to high temperatures and high carbon dioxide concentrations. And the Vostok ice core eventually went back to over 800,000 years, but here's just the first half of the Antarctic ice core from Vostok. Very strong correlation between temperature and carbon dioxide. So let's look at the maximum glacial glaciation during the last ice age about 18,000 years ago. So the northern hemisphere was certainly gripped in this ice age, and you had the Laurentian ice sheet in Canada, which extended all the way down into the Midwestern United States, all the way down to almost the town that I lived, or almost to the Kansas City, which is where I grew up in the Midwest. And much of Europe was under a very thick ice sheet as well. So here you can see that the Laurentian ice sheet extended all the way down into Iowa and northern Missouri and right over to Kansas City where I grew up. And so why did we have this great climate fluctuations in the past when that obviously wasn't caused by humans? Well, there's a theory to describe the timing of the ice ages, and that is Milankovitch theory. And Milankovitch theory successfully predicts the timing of the ice ages over the last 800,000 years. And so what Milankovitch basically came up with is that there are orbital parameters and reasons why we go into ice ages. So we look at how the tilt of the Earth's axis changes. It wobbles back and forth from about 22 degrees to 24.5 degrees. That is still, the planet is ringing from the collision that it had with a Mars-sized planet early on in the formation of the solar system. The Milankovitch theory also looks at the precession of our northern pole, our precession of our axis, that the Earth basically wobbles like a top, and that will impact the time of year when we are closest to the sun, whether we're there during our northern hemisphere winter or northern hemisphere summer. And then we have the eccentricity of the Earth's orbit, which changes over time. That elliptical eccentricity, 0.0167, that we used previously, changes over time due to the tugs, however small they might be, of Jupiter and Saturn can alter the Earth's orbit on longer timescales. So this slide is showing the progression of the Earth's axis due to precession. And right now, the North Pole is pointing at Polaris, which what we call the North Star. But the precession of the Earth will cause the North Pole to be pointing at a different star in the future. So right now, the Earth happens to be closest to the sun in the northern hemisphere winter, but 11,500 years from now, the Earth will be furthest from the sun in the northern hemisphere winter due to the precession of Earth around its axis. So what this really does is it changes the season at which we are at close proximity to the sun. So here we have the effect of the changing tilt. So right now our declination is around 23.5 degrees. That's our current situation. And 10,500 years from now in the future, we'll be at 22.1 degrees declination. And 10,500 years ago, we were at 24.5 degrees. So you can see that there's this progression. This is about a 42,000 year period where we go from a larger tilt to a smaller tilt. And as I mentioned earlier, this wobble in the tilt is a result of the collision that happened between Earth and a Mars-sized planetoid body back during the formation of the solar system. So the question that I have is, which of these declinations will cause the strongest seasons? Well, if we had no tilt at all, at 0 degrees declination, we would not have seasons. We would have essentially the same day length and the same sun angle year-round. So it stands to reason that as the declination gets progressively larger, the seasonal differences in the amount of solar radiation that's received at a given point on the planet will be changing as well, will be much larger. And of course, the absolute largest seasonal differences that you could have would be if you had a declination of 90 degrees. And we do have one planet in our solar system that has a declination of 90 degrees. So here we have the essentially 100,000 year orbital eccentricity cycle. And so the question is, and remember that this change in the eccentricity of our orbit is basically caused by gravitational interactions with Jupiter and Saturn. So which of these orbits will cause the strongest seasons? Well, you'd like to vary the difference. You'd like to have a significant difference in the amount of radiation that you receive in one season versus another. So the stronger the more elliptical the orbit, the bigger the difference that you can have between the amount of solar radiation that you receive at one time of the year versus another. So the greater eccentricity orbit will cause the stronger seasons. So, although the Milankovitch theory really kind of predicts the timing of the ice ages, if you do the calculations on how these orbital variations actually change the amount of radiation that we receive, it's not sufficient to cause an ice age or to bring us out into an interglacial. So as a result, we have actually identified what we call positive feedback mechanisms that amplify the effect from the orbital parameters of the Milankovitch theory in order to drive us into or out of an ice age. So by a positive feedback mechanism, I'm not talking about something that's good or bad. What I'm talking about is something that reinforces the initial change. So here, for example, if the atmosphere happens to cool because we get slightly less radiation from the sun, that will lead to less melting of snow, especially if that cooling occurs during the summer. So if we have more snow at the end of the summer, then that will increase our albedo, or our reflectivity. And that higher reflectivity will cause the atmosphere to cool, which will lead to less melting of the snow, which will increase the albedo, which will then cool the atmosphere more. And you can see that if you leave this process unchecked, then you would actually end up with a completely snow-covered Earth. So this positive feedback mechanism is trying to drive the Earth to the snowball Earth scenario. But there are negative feedback mechanisms that put the brakes on these positive feedbacks as well. So negative feedbacks are not intended to be positive or negative, good or bad. They just tend to not reinforce the initial change. So for example, let's say that we had a situation where the atmosphere warmed slightly due to an increase in the amount of radiation from the sun. Well, that would cause evaporation from the oceans to increase because of the increased saturation water vapor pressure. And these higher humidities in the atmosphere would lead to more clouds. But if you have more clouds, that's going to increase the reflectivity of the planet, which is going to cause the atmosphere to cool, which is in the opposite direction of the initial change, which was in warming atmosphere. So this cloud feedback mechanism would actually be a negative feedback mechanism and would put the brakes on continued rampant runaway warming. So the climate system has hundreds of these positive and negative feedback mechanisms, and I liken it to a tug of war, where you have very strong forces on either side. You have positive feedback mechanisms that are trying to push us away from our current climate, and you have negative feedback mechanisms which are trying to preserve the certain climate. But what we all know is that tug of war rarely ends with a slight movement of the red flag in the middle. It often comes with one side overwhelming the other. And that's what we're concerned about with potential climate change, is that we might reach a tipping point at which the climate does a rapid shift to a new equilibrium. So what's going to happen to our climate in the future? Well, Milankovitch theory predicts that the Earth will enter a new ice age within the next 2,000 years. However, humans have altered the chemistry of our atmosphere and have dramatically increased the concentration of greenhouse gases. And our modeling basically suggests that the Earth's climate is headed toward an unprecedented warming period caused by these greenhouse gas concentrations, and it may in fact prevent the next ice age from happening at all. So let's take a look at what's going on. So here we have the temperature variation over the last 18,000 years when we came out of the Ice Age. And then over the last 11,000 years, we have the Holocene epoch, which is essentially all of human history. And you'll notice that the temperature was pretty constant during this time period, abnormally so. And so was the carbon dioxide concentration. But you can see the dramatic rise in the carbon dioxide concentration here in the last 150 years. In fact, this chart's a little bit old, and the current carbon dioxide concentration is greater than 410 parts per million by volume. So it's definitely off the chart there. And the strong correlation between carbon dioxide and temperature is something that has scientists very concerned that if that correlation were to continue moving forward with much higher CO2 concentrations, then we would end up with a dramatic increase in the temperature of the system. And now that the carbon dioxide concentration is up over 400 parts per million, we can say that from all of the ice core data that we've looked at, that the carbon dioxide concentration in the Earth's atmosphere is now higher than it has been any time in the last 2 million years. So what do we know about the temperature of the Earth? And here we're looking at the global and hemispheric annual temperature anomalies. So these are temperature anomalies from the average. And so the average temperature of the Earth really has increased by about 0.5 degrees Celsius in the last 100 years. And what this data is showing is that the increase is happening in both the northern and southern hemispheres, but is more pronounced in the northern hemisphere, which makes sense if this were driven by carbon dioxide, because most of the people and most of the industry are actually in the northern hemisphere, and the concentrations of carbon dioxide are actually higher in the northern hemisphere than they are in the southern hemisphere, because it takes decades in order to mix the carbon dioxide globally from the northern hemisphere to the southern hemisphere. And the increases, if you look at them, are also happening both over the land and the oceans. If you look at the temperatures over the oceans, they're rising. They're not rising as fast as over the land because the water takes more energy in order to change the temperature, but it is changing. And the land is changing faster. And you combine those together to get the top chart, which is represented from the data on the previous slide as well. So what evidence do we have that the climate is changing and that the atmosphere is warming? Well, we have noticed that the tropics are expanding. Remember when I said that the meteorological definition of the tropics was about 30 degrees north and 30 degrees south, because that's where we had the transition from the easterlies trade winds to the westerlies? Well, that transition region between the easterlies and the westerlies is moving away from the equator. And this was actually documented in a paper written by one of the faculty members at the University of Utah in the Atmospheric Sciences Department, Dr. Thomas Reichler. We also know that the stratosphere is cooling. We get this information from the Raywinson balloons. So why would the stratosphere cool? Well, if the troposphere was getting deeper because of the increased warming of the atmosphere, then that would cause the tropopause to move to a higher and higher altitude. And if you move to a higher and higher altitude, that means that the temperature of the stratosphere is going to be cooling. We know that glaciers around the world are melting, and we know that the sea level is rising due to the melting of the glaciers that are grounded on the land surfaces. Most of the sea level rise right now is occurring due to melting of Greenland, but what's scary is that there's a lot of melting going on in Antarctica now, especially in the West Antarctic Peninsula, that is starting to contribute to sea level rise. If Greenland were to completely melt, it would raise the sea levels by about 27 meters. If all of Antarctica were to melt, it would raise the sea levels by more than 200 meters. So there's a lot of potential here to change sea levels over time. It's going to take a significant amount of time to melt these massive ice reservoirs, but that is the trend that we are looking at right now. The climate debate, I always like to formulate the debate into these three questions. First of all, we'll look at the data to see, is the Earth's climate warming? And I've already showed you some of that data. And then the second question is, is this change in the Earth's climate caused by human actions, or is it naturally occurring? And one of the ways that we try and address this issue is using computer models, global climate models. We can't have two Earths and treat one as a laboratory experiment and one as a control. So we have to create this environment in global climate simulations. And what we found is that if we run the global climate simulation forward without the increased greenhouse gases caused by human activities, we cannot reproduce the temperatures that we've seen over the last 100 years. It's only by including this anthropogenic or human-caused extra heating through the greenhouse effect that these climate models can reproduce the observed temperatures over the last 150 years. So if you ask atmospheric scientists, there's really no doubt that the change in the Earth's climate that we've seen over the last 100 years is due to our human actions. And then the third question is actually a political one, is what actions, if any, should we take if the climate change is caused by humans? There are arguments that would say that climate change will be good for some regions and poor for others. It could have devastating consequences in some areas, and it might benefit other areas. So we actually have to try and understand how the climate will impact the different regions and then make political decisions on whether or not those outcomes are acceptable or not. And if those outcomes are unacceptable on a global basis, then we need to take action now to try and stem the tide of what the computer models are showing will be a pretty significant warming over the next 100 or 200 years.